Hello pre-calculus students, this is Miss Robinson and I will be going through 1D, example 1D with you in section 4.5 notes right now. So please follow along. Again, we are using the same 7 steps that we've been using for analyzing the graph of a rational function. So we can just continue with this. Okay. So this time our rational function, r of x, is x squared minus 9, all divided by x squared plus 9x plus 18. Okay, so let's go through our steps. Step 1, if we look back, asks us to factor the numerator and denominator of our rational function. So first step is to factor. So let's look at our numerator, x squared minus 9. We know that this is a difference of squares, so that's x plus 3 times x minus 3. And that's it for my numerator, right? That's as simplified as it gets. Then we look at our denominator. We know that our denominator, x squared plus 9x plus 18, is factorable. 6 times 3 gives us 18, and 6 plus 3 gives us 9. So we would know that our factors are x plus 6 and x plus 3. Okay. So we factored numerator, denominator. But there was an extra part to step 1. Step 1 also asks us to find the domain of the rational function. So let's find the domain. So we know our domain is all of the x values with exceptions, wherever we cannot plug in x values and get a defined y value. So if we look at our function, we know we have an issue where our denominator equals 0. So where each factor is equal to 0 on our denominator. So this factor here tells me that x cannot equal negative 6. And this factor here tells me that x cannot equal negative 3. And those are the only problems we're seeing right now. Okay. If I want to write this in interval notation, I can also write this as negative infinity to negative 6, union negative 6 to negative 3, union negative 3 to infinity. Again, either method works. Next step, step 2. So if we look back at step 2 asks us to write our rational function in lowest terms. In other words, to simplify. So if we look back at our rational function, we see that we can actually simplify this time. There is an x plus 3 on the numerator and an x plus 3 on the denominator. Now, most of you would just automatically cancel this right away. You would say, oh, wonderful. Can cancel all this x plus 3 that I have here. But you need to be really careful when you simplify this, because in the original function, those x plus 3's are still included. So you need to be very careful when you simplify, and make sure that you do this in a separate step like we're doing it right now, so we can make note of the fact that we simplified. So we would say that our new simplified rational function, dividing out these x plus 3's, just leaves us with x minus 3 on the numerator, and x plus 6 on the denominator. Okay. Now, right now, we remember that. Actually, we'll do this in a later step. Just remember, pay attention to the fact that you canceled this x plus 3 out. Okay. We make note of it in a separate step for a reason, and we'll see that in a moment. Okay, so let's move on to step 3. Step 3 asks us to locate the intercepts of the graph. So we'll start with x-intercepts. So x-intercepts where y equals 0 or where our numerator equals 0. So if we look at our simplified version here, we see that our numerator equals 0 when x equals 3. So we have an x-intercept at x equals 3. Okay. Y-intercepts where x equals 0. If we plug in 0 for x, we see 0 minus 3 over 0 plus 6 leaves us with negative 3 over 6, or y equals negative 1/2. So we have a y-intercept at y equals negative 1/2. Okay, takes care of step 3. Step 4 was to locate the vertical asymptotes. Okay, so step 4. My vertical asymptotes. Now we remember that Our vertical asymptotes are where we have issues with our domain, right? Now, this is where this problem gets a little bit trickier. So here, we identified that we had issues with our domain at both -6 and -3. But after we simplified, wrote our lowest terms rational function, we see that we only keep the issue, the undefined y values, at x equals -6. This simplified version here is what gives us our vertical asymptotes. So this one right here tells me that I just have a vertical asymptote at x equals -6, because that's my only problem in this function for my domain, for my x values. However, in our original, we were not allowed to define a value at -3. If we look at the simplified version, sure, I can tell you where -3 is headed. I can plug -3 in here and have an idea of where it is supposed to be. However, in our original function, we are not allowed to plug in a -3 because we will divide by a 0, which is a problem. So we still have to exclude this x equals -3. It's just not an asymptote because we know where it's supposed to go. Okay? If you remember, these places where we technically needed to exclude a value, but we knew where we could define it at, is called a hole. So we would say that we would have a hole at x equals -3. And we can actually plug in this -3 into the simplified function and see where it should be headed. So if I plug in -3, -3 minus 3 gives me -6. -3 plus 2 gives me +3, which is a -2. So I know that I have a point at -3, -2 that should be a hole. Okay, so yes, my function should technically go through this point. I can consider it as going through this point. However, it cannot touch this point exactly. It approaches this point, it is going in that direction, but I still cannot define it because of my original function at x equals -3. And we'll see this later when we're graphing. Okay, so that's step 4. I've ran out of room on this side of the paper, so I'm going to move to the back side of my paper. Okay, if you have room, that's fine. You can also get another sheet of paper. I'm going to rewrite my function. Okay, so I have my rational function is x squared minus 9 over x to the 4th minus 1. And we also simplify that later to be I wrote the denominator wrong, I'm sorry. X squared minus 9 over x squared plus 9x plus 18. And we simplify that to be x minus 3 over x plus 6. Okay. So I'm just rewriting that to remind myself of what my rational function is. We are moving on to step 5 now. Step 5, if we look back at our notes, asks us to locate the horizontal or oblique asymptotes. So horizontal or oblique. If we remember, the way to decide that is if we have an improper fraction, meaning that our numerator and denominator either have equal degree values or our numerator has a greater degree than our denominator, which is the case here. You can see that these are equal degrees. So if this is the case that we have this improper fraction, then we need to divide. Okay, since these are square values, we need to use long division. So we're going to take x squared minus 9 as our dividend and x squared plus 9x plus 18 as our divisor. Okay, and then we're going to divide. X squared goes into x squared one time. X squared times 1 is x squared. Multiply x squared plus 9x plus 18 and subtract. These cancel. I'm left with negative 9x minus 27. Okay, X squared does not go into negative 9x, so that becomes my remainder. Okay. Now, if I look at this, or if I look at this, I can see that I actually have some like terms to cancel out. Now, I probably could have prevented this early on, right? I divided by my original term, but if we consider, we really divided by more originally, right? We divided by that x plus 3 in each of these. So it actually would have been smarter for me to divide these first. Here, I can look at these, and I can see that they both have an x plus 3 in them, if I want to divide those. But if I had originally divided x minus 3 by x plus 6, I wouldn't have this complicated remainder here. Here, x goes into x one time, multiply, and that's x plus 6, subtract, and I'm just left with negative 9. Okay. I could see up here that if I divided this numerator by negative 9, I would be left with x plus 3. As well, the denominator is x plus 3 times x plus 6. Same remainder. So this goes to show you that in this problem, if I have something canceled out, when I want to find my horizontal and oblique asymptotes, I shouldn't really be using the original. I should be using the more simplified terms because we've already divided things out. You can see this. Okay? So yes, you can use this and you will get the same answer. However, you will have more work to do simplifying than I had in this problem. Okay. There's also a considerable amount more terms to be multiplying and subtracting here. Okay. So use the simplified terms when you want to divide for that horizontal and oblique asymptote. Okay. Alright, so when we divided, we got 1. We know that our horizontal and oblique asymptote is our quotient. If it's just a number, we know we have a horizontal asymptote at y equals 1. Again, it's not at just 1, it's at the equation y equals 1, so do not forget that y equals. If we have a horizontal asymptote, we do not have an oblique asymptote, so none there. Now we want to see if that, or my function is ever going to cross this horizontal asymptote. And remember earlier we said that we can plug it in to our function. So I can set the y values of my function equal to 1 and solve. I would solve by multiplying by x plus 6 and simplifying. Here we see that we are left with 6 equals negative 3. Does not work. So this would tell me I do not have an intersection. We could also, from what we saw before, set our remainder equal to 0. So over here I can say, can negative 9 ever equal 0? Not going to happen. No intersection. So again, either method you would like to use, both are sufficient. This one's a little bit more conceptual. Same idea. Okay, so we know that there is no intersection of my horizontal asymptote y equals 1. Okay, good. Moving on to step 6. If we look back at our notes, step 6 asks me to graph the rational function using a graphing utility. So I'm going to take out my graphing calculator, clear out any functions that I have from earlier, and I'm going to type in my original function. Remember, we want to type in this original function, otherwise we won't be able to test for things like holes or test our own work. Okay. Also, be very careful with your parentheses. Make sure you're putting them in appropriate places, otherwise you might not be getting the graph that you would like to see. Okay. So we plug in our function. I usually like to start with a standard window. We'll just go -10 to 10, -10 to 10, and graph. Alright, so I am seeing a good deal in my function, but this is cutting off over here. I want to see a little bit more of this, so I'm going to change my function a little bit. I'm maybe going to go from -15 to +15. Okay. Much better. I get to see more of what's happening over here, and a little bit more even of what's happening on this side as well. Okay, so now let's check things a little bit. So first we want to check that we have, if we look here, an x-intercept at x equals 3. So if we look here, I can kind of glance and see that, yes, I have an x-intercept around x equals 3. That's just glancing. I can also use my table to tell myself exactly. So 3 is 0. Good. And I should also have a y-intercept where y equals -1/2. So if I go to x equals 0, good, I get -0.5, -1/2. Alright, keep checking. I should also see that I have a hole at x equals -3. So if I go to -3 for x, I should see an error. Perfect. Now I should only see an arrow at -3 because it is not an asymptote. It's a hole. Okay. But I should still be seeing that error. Okay. And then I also have an asymptote at -6. So I can check here as well. -6. Perfect. Okay. And then I have a horizontal asymptote at y equals 1. So I can check in this direction. If I decrease my x, I see that my values are getting smaller and smaller. So I can move closer and closer to 1 and see what's happening here. You can see I am getting closer and closer to 1, slowly reaching 1, but not exactly hitting that 1. I see it's decreasing very slowly towards 1. And then if I want to go in the other direction, so here, as we increase our x, again we can see that we are getting closer and closer to 1, a little bit faster in this direction. However, we are getting much, much slower now. Still not even hitting 0.9. So just slowly, slowly increasing towards 1. I am not seeing an intersect 1. Okay, so good. We've checked some of our work. We've been able to use this graphing utility the way we should be. Now we just need to write down our window for this step. Okay, so step 6. We used an x minimum of -15 and an x maximum of 15, a y minimum of -10, and a y maximum of +10. Okay. Our final step, step 7, if we look back at our notes, is to use the results from steps 1 through 6 to graph the rational function by hand. Okay, so first we are going to make our grid. Okay, then we're going to go through each piece of information that we've obtained. Okay, so step 1 we were just factoring, finding domain. Step 2 simplifying. Step 3 we have actual things to plot. So we have the point 3, 0 for an x-intercept, so we should plot that. +3, 0, make sure you're labeling. Then we have a y-intercept at y equals -1/2, So we have 0, negative 1/2 right here. Okay, again, make sure you're labeling. Anything you write down, you should label. Okay. And then we see we had this vertical asymptote at x equals -6. So we want to graph that. So we have 1, 2, 3, 4, 5, -6. And we want to label this x equals -6. Okay. And then we had a hole at -3, -2. This is why it's important to actually find this value where you have your hole, because this is a point you should be plotting. It's not an asymptote where we can draw the line. It's a point, so we need to have both values of the point in order to show this accurately when we graph it. So we can actually plot the point, -3, -2. Okay. Just use this open dot here. We really exaggerate when we graph it on our graphs here. We, strictly speaking, know that on our graphing utility, like we've seen before, it's not exactly visible as it's a point. I mean, points are infinitesimally small, so we can't exactly visualize them when we're looking at a graph, but when we draw our graphs, we like to make sure that this is visible upon glancing. So we really make this large open circle so we can really emphasize that there's a hole at this point. Okay. And then if we keep looking at our information, we see up here we had a horizontal asymptote at y equals 1, so we should be drawing that as well. Okay. So y equals 1, we have this horizontal asymptote. Now this is really all of the information that we had, but we can use this to draw a good deal of our graph. So if I look at this right side of my graph, on the right side of this vertical asymptote x equals -6, I see that I should not be crossing this horizontal asymptote, and I should not be crossing this vertical asymptote, and I should go through all of these points that I have here. So that gives me this graph right here. Okay. Now on this side, again, I also know that I cannot cross this horizontal asymptote, where we decided that there is no intersection with a horizontal asymptote, so we should not be able to cross it. We can never cross a vertical asymptote, so we can't cross here. So either my graph is here or here. If my graph was down here, we would be assuming we would have an x-intercept. We do not, so that tells me that my graph should be up here. So I should have something along these lines. I can plot points to determine better accuracy. However, I know that generally my graph should be moving closer to the vertical asymptote and the horizontal asymptote as I get closer to those x values. Okay. Again, we're making sure that we label all points that we plot, all asymptotes that we plot. Okay. Now that's it for step 7.